Coordinate proof. Many geometric properties can be proven by using a coordinate plane. A coordinate proof is a proof that uses figures on a coordinate plane to prove geometric figures. To prove geometric properties using the methods of coordinate geometry, we consider certain guidelines for placing figures on a coordinate plane. First, use the origin as vertex or center of a figure. Second, place at least one side of a polygon on an axis, either the x or the y axis. If possible, keep the figure within the first quadrant. Remember, in first quadrant, our x and y coordinates are both positive. And lastly, use coordinates that make computation simple and easy. Sometimes, using coordinates that are multiples of 2 would make the computation easier. Let us have example. Let us prove that the midpoint of the hypotenuse of a right triangle is equidistant from the three vertices. So the given is a right triangle ABC, and point D is the midpoint of the hypotenuse. And we need to prove that the line segment AD is congruent to line segment DB and also congruent to line segment CD. So here is our figure. We say that this right triangle ABC has a midpoint at point D. So let's say this is point D. And we need to prove that the line segment AD is congruent to the line segment DB and also congruent to line segment CD. So for point C, the coordinates are 0, 0 because this point C is found at the origin. Our point A will be 0, 2B. So in that case, let us say this one is point A, this is B, so that is why we have B plus B is 2B. And since we form here a vertical line, the common coordinate between point C and point A will be the x coordinate. That's why we use 0, 2B. And for point B, let us say this one is A. Since this is equal to the other side, so this is A plus A, so we use 2A, 0. So it becomes 0 because we form here a horizontal line. So the common coordinate will be the y coordinate, that is 0. So we have point A with coordinate 0, 2B. Our point B with coordinates 2A, 0. And of course, the point C with coordinates 0, 0. So for our proof, so again, this is our given figure. We've used the midpoint formula. The coordinates of the midpoint D, so here, this one will become our point D. So finding the midpoint for point A and point B, again, we use x sub 1 plus x sub 2 over 2 and y sub 1 plus y sub 2 over 2. So we have 0 plus 2a over 2. And for the y coordinates, we have 2b plus 0 over 2. 0 plus 2a is 2a, and 2a over 2, they are both divisible by 2. So we have simply a. And then 2b plus 0 is 2b. 2b plus 2, they are both divisible again by 2. So the remaining will be b. So the coordinates of the midpoint D will be A and B. So again, we have point D with coordinates A, B. And then using the distance formula, again that is D equals the square root of the square of x sub 2 minus x sub 1 plus the square of y sub 2 minus y sub 1. Let us prove that the line segment AD is congruent to line segment DB and also congruent to the line segment CD. So therefore, we need to take that the length of the line segment AD, line segment DB, and line segment CD are equal. So let us use first the line segment AD. So we have here A minus 0 squared plus b minus 2b squared. Getting its square root, so we simplify this. We have a minus 0 is a, and then square. A times a is a squared. B minus 2b is negative b, and then square of that, negative times negative is positive, and then b squared. So we have the length of the line segment AD will be the square root of a squared plus b squared. Let us now have the length of the line segment DB. Using again the distance formula, so we have here 2a minus a squared plus 0 minus b squared, and getting its square root. So we have 2a minus a is a, and then square root of a is a squared. 0 minus b is negative b, and then negative b times negative b is positive b squared. So we still have the square root of a squared plus b squared. And then finally, we have the line segment CD. Using again the distance formula, we'll have a minus 0 squared plus b minus 0 squared, and getting again its square root. So a minus 0 is a, getting its square is a squared, b minus 0 is b, and the square of b is b squared. So we have again the square root of a squared plus b squared. Since the line segment AD is congruent to the line segment DB and also congruent to the line segment CD, then our point D is equidistant from the three vertices. Another example, the segments joining the midpoint of consecutive sides of an isosceles trapezoid form a rhombus. So let us say this is our isosceles trapezoid. So the isosceles trapezoid has two opposite sides. So the given line segment AC and line segment GE, they are two opposite sides that are parallel and two other sides that are equal in length. So the line segment AG and the line segment CE. So given this isosceles trapezoid ACEG with again the line segment AG that is congruent to line segment CE. And then from here, we have point point D, F, and H that are midpoints of the sides of the trapezoid. So for line segment AC, point B will be the midpoint. For line segment CD, the point D is the midpoint. For the line segment GE or EG, point F will be the midpoint. And for the line segment AG, point H is the midpoint. Now we have to prove that this quadrilateral HBDF is a rhombus, which means all sides are equal. So let us name first the missing coordinates of this given figure. Let us draw our x and y axis. So let us say our given figure lies on both the first and second quadrant. So for point F, so this is our point F, the coordinates will be 0, 0 because it is found at the origin. And then for point E, we have A, 0. Let us say this one is A, and since we form a horizontal line here, the common coordinate between point E and point F will be the y coordinate. So since the y coordinate of point F is 0, its y coordinate of point E will also be equal to 0. And then since we have here a bisector, meaning this side is congruent to this side. So we can say that this is also A, but since it is located on the second quadrant, the sign of the x coordinate in the second quadrant is always negative. So we use negative A, 0. And then for point B, let us say this is A and this is B. This one will become C. And since we form here a vertical line, meaning what is common between point B and point F will be the x coordinate. So that is why we have 0, C. And then for point C and point A, we have to draw first our given line here. So in this case, this one is the same with this. If this is point A, we can say that this one is point B. And the common coordinate between point B and point C, since we form a horizontal line, will be the y coordinate. And its y coordinate is point C. So we can say that the coordinate of point C will be B, C. And the same thing with point A. From point B to point C, this is the same with our point A to point B. But again, it is located in the second quadrant. So our x coordinate here becomes negative B, C. So for our point D, since the line segment CE has its midpoint at point D, we can take its midpoint by applying again the midpoint formula. That is x sub 1 plus x sub 2 over 2 and y sub 1 plus y sub 2 over 2. So we can have B plus A over 2 or A plus B over 2, and C plus 0 is C over 2. The same idea with the line segment AG. Point H will be the midpoint, so we get the midpoint between this point A and G, or the midpoint of the line segment AG. We have negative B plus negative A, or it's simply negative A minus B over 2. And then we have C plus 0 is C over 2. So we have already completed the coordinates of our given figure. So let us now prove by using distance formula. So let us prove that the line segment HB is congruent to line segment BD and also congruent to line segment DF. The same thing with the line segment HF. So again, this is our given figure a while ago. So first, let us have the line segment HB. So the distance between point H and point B. So we have here 0, x sub 2, minus the x sub 1, that is negative a minus b over 2 squared plus c minus c over 2 squared. So in this case, we simplify first the terms in this grouping symbol. So we have negative times negative is positive a, negative times negative b is positive b. So we have here a plus b over 2 squared. So we have the square of the binomial. So we can have here, a squared plus 2 times a times b is 2ab. And then the square of b is b squared. And then we distribute also the square for our 2 in the denominator. That is 2 times 2 is 4. So we have again the square root of a squared plus 2ab plus b squared over 4. And then in this case, we have c minus c over 2. So it becomes 2c minus c is c over 2. So c times c is c squared and 2 times 2 is 4. And then we can still simplify this one. Since we have here similar fractions, we have common denominator of 4. So we can have a squared plus 2ab plus b squared plus c squared all over 4. And getting the square root, our 4 is a perfect square. So we can get the square root of that. So the length of the line segment HB will be the square root of a squared plus 2ab plus b squared plus c squared over 2. How about the distance between point B and point D? So again, using the distance formula, so our point B to point D, so we have a plus b over 2 minus 0 squared plus c over 2 minus c squared. So we can now cancel this one. And then we have a times a is a squared. 2 times a times b is 2ab. And then b times b is b squared. The same thing with the denominator. We get the square. That is 2 squared is 4. So again, we have the square root of a squared plus 2ab plus b squared over 4. Now for c over 2 minus c, this one will become negative c over 2. And then negative times negative is positive. That's why we have c squared. And then 2 squared is equal to 4. So again, we have similar fractions. We can now combine the numerators. So we have a squared plus 2ab plus b squared plus c squared all over 4, getting its square root. Square root of 4 is 2. So we have the length of the line segment BD as square root of a squared plus 2ab plus b squared plus c squared over 2, which is the same with the line segment HB. What about the distance between the point D and point F, or the length of the line segment DF? So again, using the distance formula, we have the point D and the point F. We can have 0 minus a plus b over 2 squared plus 0 minus c over 2 squared. So getting its square roots. We simplify first. This one will become negative a minus b over 2, and then we square. Negative a squared, that will be positive a squared. Negative b times negative b is positive b squared. And then this one becomes positive 4. So we have there square root of a squared plus 2ab plus b squared over 4. And then 0 minus c over 2 will become negative c over 2. Then getting it square, negative c times negative c is positive c squared. And then 2 squared is 4. Again, we have formed here similar fractions. We combine the numerators. We'll have square root of a squared plus 2ab plus b squared plus c squared over 4. But since our 4 is a perfect square, we can get its root by having the length of the line segment DF square root of a squared plus 2ab plus b squared plus c squared over 2. And then lastly, we need to find for the distance between point H and F. or the length of the line segment HF. Again, using the distance formula, we have 0 minus negative a minus b over 2 squared plus 0 minus c over 2 squared. And then we get again the square root. Simplifying this one, this will be negative times negative is positive a, negative times negative is positive b, and then we have a plus b over 2 squared. So a squared is a squared, 2 times a times b is 2ab, b squared is b squared, and then 2 squared is 4. So we have the square root of a squared plus 2ab plus b squared over 4. And on the other side, we have 0 minus c over 2. It becomes c, negative c over 2, getting it square. Negative c squared is positive c squared, and 2 squared is equal to 4. And we have formed again similar fractions. We add the numerators. So we have a squared plus 2ab plus b squared plus c squared over 4. And then we take the square root. So since 4 is a first square, we can get its square root, that is 2. So the line segment HF will be equal to the square root of a squared plus 2ab plus b squared plus c squared over 2. So since we have proven that the line segment HB, its length is equal to the length of the line segment BD, the same with the line segment DF and line segment HF. So the given quadrilateral HBDF will be a rhombus. How about in finding the missing coordinates given the figure? So again, as like what I have said a while ago, we have to check what will be the common coordinates between the two given points. So again, this point is located at the origin, so this will become 0, 0. So since this point and point B, we form here a horizontal line. So if we are forming horizontal line, it means the y-coordinate will be the same. So the y-coordinate here will be 0. So this one will become 0. And its x-coordinate, so knowing that this is point A here, so as we draw an imaginary line, so this one is point D. This side or this part is equal to this 1. So this is D. So D plus another D will become 2D. So the coordinates of point B will be 2D, 0. The next, we have our square. So for the square, all sides are equal or congruent. So this one will again 0, 0 because it is found at the origin. And then for point A, we have 0, B. And then for point B, since we form here a horizontal line, meaning their y-coordinate will be the same. So here, our y-coordinate will become B, and our given x-coordinate, since this side is equal to this side, and the same thing with the other two sides, because in our square, the four sides are equal in length. So this one will become B also. So for point B, the coordinates are B, B. And then for C, again, since this point to this point we form a horizontal line, its y-coordinate will become 0 because the y-coordinate rather of this origin is 0. And for point B and point C, we form here a vertical line, meaning their x-coordinate, the x-coordinate of point B is B. So this point C will have its x-coordinate as B. So we have B, 0. Then for a rectangle, so we have, again here, this is at the origin. So we'll have here 0, 0. So in rectangle, opposite sides are equal. So this line segment AB will be equal to this line segment, and the same thing with this two given line segment. So if point A is 0, B, so for the point B here, we form a horizontal line. So what is common between point A and point B will be the y coordinate. So the y coordinate of point A is V. So its y coordinate will also be equal to V, and then its x coordinate will be, since this line segment we form here a vertical line, so what is common is the x coordinate. The x coordinate of our point C is u, so this will become u, v. And then for our point C, its y coordinate is the same with the y coordinate of this point, since we form a horizontal line. So knowing that this one is at the origin, it is 0, 0. So the y coordinate of the point C will also be equal to 0. So we have C with coordinates u, 0. And then with parallelogram. So in parallelogram, the two pairs of parallel sides, and then we have opposite sides are equal in length. So again, this one is at the origin, so this will be 0, 0. And then for our A, so we have A with our x coordinate, which is m. And then for our given y coordinate, since we form our horizontal line, so the point A and point B will have the same y coordinate, and the y coordinate of point B is q, so we'll have here point A with coordinates m, q. And then for our B, so if we draw an imaginary line here, since this one is point K, let us draw again a line here. That means from this point to this one, this is already our M. And this length or this side is equal to this side. So that means this one is also M. So we can have here, since this is already K and this is M, the x coordinate will become K plus M, and then our y coordinate is Q. And then lastly, for point C, we form a horizontal line. So the y coordinate is the same with this point, which is 0. So our C has coordinates K, 0. And then we have a trapezoid. So in trapezoid, one pair of parallel sides. So this one is parallel to this side. So again, this is at the origin, so the coordinates are 0, 0. And then for point A, since we form again a vertical line, what is common between this point and point A will be the x coordinate. Since the x coordinate of the origin is 0, so our point A will have 0, B. And then our B is F, G. So in this case, for point C, again, for our x coordinate and y coordinate, we form here a horizontal line, meaning this point C and this point at the origin will have the same y coordinate. So the y coordinate here becomes 0. And since point B and point C, we form a vertical line, so what is common is the x coordinate, which is F. So that's why we have point C with coordinates F, 0. So this one is point C. And then let us say we have the isosceles triangle. The given triangle is found both in the first quadrant and the second quadrant. But we know that in isosceles triangle, the two sides have equal length. So this line segment AB is congruent to line segment BC. So to find this point A rather. So the given point C is A, 0. So since point A is, we form here a horizontal line. So what is common again is the y-coordinate. So the y-coordinate here is 0, and the x-coordinate, since this side is equal to this one, so this is also A. So because from this point to this point C, we have A. So meaning from this point to point A, this is also A. But since it is located on the second quadrant, the sign of the x-coordinate in the second quadrant is negative. So we have here negative A, 0.